Okay, we can look at some solutions to the questions in this worksheet on periodic motion. So the first question is about converting angles in degrees to radians. So converting, converting angles from degrees to radians, we need to multiply the degrees with pi over 180. And the conversion of angles from degrees to radians is a recipe. The multiplication with pi divided by 180 is a recipe that can be applied to any angle. There's no exception to the rule. So maybe we'll just pick out some angles here, and we don't need to convert all four angles because the procedure is the same. And so you can do some. So maybe I'll pick negative 12 degrees and maybe 135 degrees. So maybe let's convert these two angles. So negative 12 degrees, okay, that will be the angle in degrees negative. So include the negative sign as well in your conversion. So the negative sign should not disappear, but you just simply multiply that with pi and then divide by 180. And you should get a negative answer, of course, because of that negative sign, negative 0.21 radians. Okay, and then for 135 degrees, it's a recipe. So it's the angle times pi 3.1416, or it's the pi in your calculator divided by 180. That will be about 2.4 radians. That's 2.35 something, but you round that as 2.4 radians. Okay. All right, we happy with that, with two examples for converting degrees to radians? Yeah, I'll let you convert the other two just because it's the same procedure. For 30 degrees, just multiply with pi and then divide by 180. And it's the same thing for 120 degrees. It's the same procedure. So once you get the correct answers for 135 and negative 12 degrees, then that means your procedure is correct, and you can use the same procedure for the other angles. For radians to degrees, it's also a recipe. So you multiply radians with the inverse of what you did for degrees. So 180 divided by pi. Okay, so let's pick out some examples as well. Maybe one positive and one negative. So maybe 4 pi over 5 maybe looks scary, and also negative 1. Okay. So it's also a recipe regardless of what radians you're given. So for example, 4 pi over 5 radians. You simply multiply that with 180 divided by pi. Okay. If you do the calculation in your calculator, that should give you, let's see, 144 degrees. If you're not getting 144 degrees, try to put brackets here Or what you can also do when you enter the things in the numbers in your calculator, you can do 4 times pi times 180. Put a bracket there, divided by 5 times pi. And that should, think for any kind of calculator, this format of entering the numbers should give you the correct answer. Okay. And for -1 radians, right, the recipe, the -1, so include the negative sign as well, and just multiply by 180 and divide by pi. Right. Okay, so this should be relatively straightforward to put into your calculator, and you should get about -57.3 degrees. Cool. All right. Yeah. So I let you do the others because again, it's the same procedure. Once you've got the correct answers for 1 or 2 examples, then just do the same procedure for the rest of the conversion, for the rest of the angles, and you should be fine with the conversion for that. Okay, for the second question, we're given some mathematical equations or expressions describing the simple harmonic motion of an object, and we're asked to find the amplitude, period, frequency, and angular frequency of the object's oscillation. Okay. Yeah, we can do all 3. That's fine if you want, but yeah, you'll find that it's really also just a pattern. So the 2 equations for simple harmonic motion has this pattern: x is equal to a sine omega t, or x is equal to a cosine omega t. So the equation for simple harmonic motion can either be of these 2 equations here. So for the first question A, x is equal to 3 cosine. Okay. All right. So for this question here, so we're doing question A, x is equal to 3 cosine 3 pi times t. So it will be related to the second form of the equation. So if we compare, x is equal to a cosine omega t. Okay, for the amplitudes, we can really just compare these 2 equations, and you can see that the amplitude here corresponds to that, and then omega t. Let me use a different color. Omega t is the number that's in front of t, right? So yeah, so we can just pick out there that the amplitude is equal to 3 meters. So it says here time is in seconds and displacement is in meters. Okay, so it's important to put your units as well. So the amplitude should be 3 meters, and then from the equation we can pick out the omega. Omega is any number, the number that's in front of t. So that will be 3 pi. So it should be the whole 3 pi that is equal to omega. Unit for omega is radians per second. Okay. And once you have this information, you can then have the frequency, because omega is equal to 2 pi times the frequency. So if you rearrange this equation, divide both sides with divide both sides with 2 pi, then 2 pi divided by 2 pi is equal to 1. So that's equivalent to canceling 2 pi on the right side. And you have frequencies equal to omega over 2 pi. So once you know the 2 pi, once you know omega from the equation, x is equal to 3 cosine omega t, or 3 pi t, you can then calculate for frequency f. So that will be omega 3 pi divided by 2 pi. Okay, pi divided by pi is equal to 1. So that's essentially just equal to 3 over 2, or 1.5 seconds. Hertz, sorry, hertz. The unit for frequency is hertz. And then finally, the period is equal to 1 divided by the frequency. So that will be 1 divided by 1.5, or that's 2 divided by 3. 0.667 seconds. Right. Okay, for the second equation, x is equal to 0.1 sine 4t. It's the same procedure. So it's again the comparison, but it's again comparing the given equation to the form a sine omega t, but this time it's sine. So here you can again pick up the amplitude. So let me just put the amplitude should be 0.1 meters. So comparing, again, amplitude is this, and omega is the number in front of t. So omega is 4 seconds. 4 radians per second is the unit for angular frequency. So once you have angular frequency, the normal frequency f is equal to angular frequency divided by 2 pi. So that will be 4 divided by 2 pi. That will be 0.64 hertz. Okay. And frequency is just the inverse of, period is just the inverse of frequency. So that will be 2 pi over 4, or 90 seconds. 1 divided by 0.64. Wait, 4 divided by, it's not 90 seconds, it's 1.57 seconds. Okay, same deal for the third one. Minus 10 cosine 1000 t. If you get a negative sign, you have to include that negative sign as well. So your amplitude should be negative 10 meters. Okay? You need to include the negative sign, because technically speaking, if you compare that to the equation x is equal to a cosine omega t, a is this whole thing before cosine, which includes the negative sign. So remember to include the negative sign as well. And omega will be 1000 radians per second. Therefore, frequency is equal to omega over 2 pi, or 1000 divided by 2 times pi. That will give you 159 hertz. And the period will be the inverse of that, 6.28 times 10 to the minus 3 seconds. So period is, of course, 1 divided by the frequency. All right. Cool. Okay, now we are asked to sketch the graph. So we'll just sketch 2 graphs here. A and C, they're both cosine functions, so they'll just start from the amplitude, and their graphs will look similar. So let's sketch 2 graphs, one sine and one cosine. So let's start from B. Okay, so for your sinusoidal graph, the y-axis is always the displacement x in meters, and the x-axis is always time in seconds, right? And then you have there a sine function, 0.1 sine 40. So a sine function we know starts from equilibrium. So your object starts from the equilibrium position, x is equal to 0. Right, so x is equal to 0 is there, and you have this sinusoidal graph. Okay, it says we need to sketch with the correct amplitudes and all of that. So the amplitude here, so at this point, the amplitude should be 0.1 meters. Okay, of course, here on the lower side, this should be a negative 0.1 meters for the amplitude. And then the period is 1.57 seconds. So period is the distance between 2 points just before your pattern repeats. Okay, so from this point to the origin, that's the period 1.57, or is it 1.56 seconds? Okay, and so half the period will be half of that, 0.79 seconds. Right. Okay. Then you have a complete graph. You have the sinusoidal graph, and you've labeled the amplitude, the maximum displacement, and the period 1.57. So half a period is just optional to label, but at least you should label what your period is. Okay, and then for the graph of question C, so graph for question A, 3 cosine 3 pi t, it will look like this graph for question B. It's also the same sinusoidal curve that starts from x is equal to 0, but it will only change in the numbers for the amplitude. So instead of 0.1 meters for the amplitude, you put 3 meters for the amplitude for the graph of question A. And for the period, instead of 1.57 seconds, you put 0.667 seconds for the period. So yeah, but the graph will look exactly the same for A and B, just the numbers will be different. So for graph C, which is described by a cosine function, So the y-axis is also always in the displacement in meters, and the y-axis is displacement in meters and x-axis is time in seconds. So cosine function, but it's -10 cosine 1000 t, and the amplitude is -10. So that means the object should have started at -10. So x is equal to 0 is here, right? So x is equal to -10 should be below the equilibrium position. Okay? And you should have like a sinusoidal graph that repeats itself like that. Right? So you can also put that the amplitude on top, that should also be 10, but it's +10 meters. For the period, so the period, it's the distance between two successive points. So you can start from the 0 position. The graph will repeat itself at this point, right? Okay, so from the reference point, t is equal to 0. So that's also t is equal to 0. The graph will repeat itself at this point. So that means this will be your period, which we've solved to be 6.28 times 10 to the -3. Period 6.28 times 10 to the -3 seconds. Yeah. So for question C, this is the complete graph. You have a sinusoidal function, but it starts from x is equal to -10, because that's what the equation is telling us. X is equal to -10. The amplitude should be -10. And then the period should be 6.28 times 10 to the -3 seconds. Okay. Right. So there's a question here in A, which has a cosine. It will start from x is equal to 3. You're right. So in A, it's a cosine function. So it will look exactly the same as the first graph here. But this time, oh, yeah, sorry. Yeah, you're right. Oksana, it's a cosine function. Cosine function. So it's, yeah. Thanks for correcting me. So I was comparing the cosine function in A to the sine function in B. So A is actually a cosine function, which should start at x is equal to 3. So that should look like this graph. Let me draw that better. Okay. So a sinusoidal graph, which starts at x is equal to 3 meters. This is x is equal to 0 and time is equal to 0. Okay. Of course, here, this should be x is equal to -3 meters for the lowest portion of the graph. And then the period is 0.667 seconds. So period, you're measuring from t equals 0 up to the point where the graph will repeat itself. So that's one period. And the period should be 0.667 seconds. Right? Cool. Yep. Thanks for correcting me on that. I was comparing A with B. A is a cosine function, B is a sine function. So their graphs will be different. It's actually B and C. B and C, it's also, they're both cosine functions, but their graphs look different because in B, your object is starting, in A, your object is starting from a positive 3 meters, but in C, your object is starting from negative 10 meters. Okay. But they're both starting from the amplitude or the maximum displacement. Okay, thanks, Willow. See you next time. All right. And then for 4, question number 4, you have here x is equal to x naught cosine thing, the square root of k over m times t. So it's again the same thing. So for question A, what is the period, frequency, angular frequency, and amplitude of the oscillation? It's a cosine function. So comparing those two, we can pick out that the amplitude is equal to x0 meters. Okay. Omega is equal to any number that's in front of time. So that's square root of k over m. Frequency is equal to 2 pi divided, I think it's the other way around. It's omega divided by 2 pi. Right? So that will be omega is square roots of k over m, and you have 1 over 2 pi. Right? For your frequency. And period is the inverse of frequency. So we just flip the frequency from the previous question. So you have 2 pi. So flip 1 over 2 pi, you flip that will give you 2 pi. Flip k divided by m, that will give you m over k. Okay. Right. So period is just flipping the frequency. And that's that. Right. Next question. If the spring constant is increased, will the frequency of oscillation increase or decrease? So spring constant is K. Spring constant is that K. And it's talking about frequency and the spring constant. So that comes into the equation F is equal to 1 over 2 pi square root of K over M. Okay. Spring constant is this one. Notice how the spring constant is proportional to the frequency. It's directly proportional to the frequency. Even if you have the square root, frequency is directly proportional to the square root of spring constant K. And we've learned that direct proportionality means if one increases, then the other increases, right? So that means that if spring constant is increased, then F should also increase. F increases as well. And you can try that. You can try to put numbers. Say, for example, K is equal to 2 and set M is equal to 1. You can find frequency is equal to 1 over 2 pi times square root of 2. Compare that to if K is equal to 4 and M is equal to 1 still, F is equal to 1 over 2 pi times square root of 4. If you compare the numbers, you'll see that F will be bigger when K is equal to 4. So you can answer that question as well in that way by putting numbers. Now for the mass, if mass is increased, what will happen to the frequency of oscillation? So the mass also comes into this equation in frequency. Notice how the mass is in the denominator, but frequency is in the numerator. So they're in opposite sides of the division bar. That means that frequency is inversely proportional to the square root of the mass, which means that if mass is increased, then the frequency should decrease. And you can do the same thing that we did for spring constant. You can put in numbers. You can put in numbers for the mass. Say mass is equal to 2 and mass is equal to 4, keeping the spring constant the same, k is equal to 1, for example, and find the frequency and compare those two. You should see that the frequency would decrease if the mass is increased. All right. Okay, and the last question, you want to design a mass spring system for an experiment where the period of oscillation is 2 seconds. So the period is 2 seconds, and you have a spring whose spring constant is 10 newtons per meter. What mass should you use? Okay. Right, so mass and spring constant comes into the equation here. And we've answered this earlier. The period is equal to 2 pi times the square root of mass over the spring constant. So let's use that equation. Period is equal to where's that? 2 pi times square root of mass over the spring constant. So the period is given, T is given, and the spring constant K is given. We then need to rearrange this to isolate mass. So how do we go about rearranging this? I can rearrange this 2 ways, maybe. Just trying to think. Okay, so I'll rearrange this using the basic method that we learned way back in week 2, where we build the equation up, starting from what we want to isolate, and then do the reverse of the building. I think that's the easiest way to visualize how to rearrange this, because mass is tied to K via the division sign, and it's inside the square root. So the question is, how do we remove the square root and separate mass from K? And I think the easiest is to try to rebuild the equation starting from what you want to isolate. So you want to isolate mass. Mass is divided by the spring constant K. And if you look at the order of operations, bed mass, okay, so you have to build the equation starting from brackets. Technically speaking, it's the bracket mass divided by K that is inside the square root. So you do the bracket first, meaning you divide mass by K first. Okay, so you divide by K, and you have mass divided by K. Okay, and you do the exponent. Square root is equivalent to exponent 1/2. Okay, so doing the square root actually comes second to dividing with K. Right. So you have m divided by K, you do the square root. That gives you square root of m divided by K. Okay. Right? And then you then multiply with 2 pi times 2 pi. Times 2 pi. Then you have 2 pi times square root of m over K, which leads you to the equation for period. Okay. We now do the reverse operations, starting with period. Right? The last thing you did was to multiply with 2 pi. So you have to divide period by 2 pi. So you have period divided by 2 pi. Okay, and then you undo the square root. The opposite of a square root is exponent 2 or square. Or exponent 2. That means you take the whole thing, t divided by 2 pi, and raise the whole thing to the power of 2. You square the whole t divided by 2 pi. Okay. All right, and finally, the last thing you need to reverse is this division sign. So divided by k, the reverse of that should be times k. And so you have k times the whole thing in brackets, 2 pi raised to the power of 2. And that leads you back to m. So therefore, m is equal to, let me tidy this up. Yeah. So therefore, m is equal to k times t over 2 pi raised to the power of 2. Right? Thanks, Oksana. See you next time. Okay, and all you have to do is substitute. K is 10 times the period is 2 divided by 2 pi raised to the power of 2, 1.01 kilograms for the mass. All right. Okay, any questions about the worksheet solutions or the lecture or anything else? Okay, no questions. All right. All right, good. Cool. Solutions will be up on stream, and so will the recordings. If there are no questions, then I'll see you on Friday for another lecture, and enjoy the rest of your day. See you next time.